ODEs with rational function coefficients.
Thank you very much for inviting me to give a talk here at the coaching seminar. So today I'm going to talk about algorithms for solving linear differential equations with rational function coefficients. So generally speaking, I will try to explain two algorithms and we will find closed form solutions. So I divided this talk into 5 parts. So first part is introduction, then I will talk about formal solutions and exponents, but it is just 1 page. Then I will talk about our quotient method algorithm. Then I will talk about integral basis, and I will give another algorithm here. Then I will talk about 2 applications. So, closed form solutions of linear differential equations are solutions that can be written in terms of well-known functions like Bessel functions, Euler functions, and hypergeometric functions. So in the current computer algebra systems, there are great solvers to find some kind of closed form solutions. For example, we can find Bessel type solutions, we can find Euler type solutions. We are interested in hypergeometric solutions. Why? Because in the current computer algebra systems, solvers are not complete, so there are hypergeometric solutions, but some of the solvers in current computer algebra systems, they cannot find those solutions. Even if a given differential equation has hypergeometric solutions, these solvers, they fail to find those solutions. So let me define what hypergeometric solutions are. So we have...
My question about the previous slide, okay? So what would such a solver do if equations, or if the coefficients of equations are parameters, have parameters in them? Unspecified parameters.
Unspecified parameters.
Yes.
What do you mean by that? So the current solvers, what they do?
Yeah.
Unspecified parameters. So, okay, I don't understand these unspecified parameters.
Suppose there is a parameter like y prime is equal to c times y. So what happens?
Y prime is equal to c times y.
Well, c is an unknown parameter. Or c over x times y. Things like that.
I see. So I think those solvers will fail and they will return an error message. Or just simply return empty set.
Okay.
Okay, so now we will consider differential equations of second order. So input stands for input. So we have L input y is equal to 0. So this is our differential equation, and L input is a differential operator with rational function coefficients. So these are the equations that we are trying to find hypergeometric solutions. So a hypergeometric solution of this equation is a solution of this form. S of x is a hypergeometric solution, so we have exponential part times r0 times 1 to f1 function plus r1 times the first derivative of that to f1 function. So we allow algebraic functions here, and these parameters are rational numbers, and 2f1 is defined by Gauss, infinite Gauss series like this. So this is a Poheimer symbol, it is defined as raising factorials. So we are interested in finding these types of solutions of a given regular singular differential operator with rational function coefficients. Okay, so I said that there are algorithms, but sometimes they fail to find hypergeometric solutions.
Nice question. Is there a reason why you consider only this hypergeometric function? Like
the order is 2 here.
Yes, like f to 1, not any other, like f for 3 or whatever. They cannot occur, or it's too complicated. So why do you consider this one?
So maybe the answer is on the next slide.
Okay.
So we have this conjecture from Van Huy and Kunwar. So this conjecture states that every second order globally bounded equation has a hypergeometric solution or an algebraic solution. So a globally bounded equation is a differential equation which, after some kind of scaling, admits a convergent integer power series solution. So now let me give you this example. So if we go to online encyclopedia of integer sequences, so we have these numbers, Fresnel numbers, and if we consider this series here, so the coefficients are these Fresnel numbers. So this L input is the minimal order differential operator such that this is a solution. Okay, so now again I will refer one of the current solvers. If we try that solver to find a closed form solution, I mean a hypergeometric solution of this differential operator, we will find yes, it has a hypergeometric solution, and it is given by this function here. So this is exponential part times 2f1 function. So here parameters 1 over 3, 2 over 3, 1, and this function here. So
could you explain what the 2f1 means?
so 2f1 is given here.
Oh,
So
okay.
it is a series. It is defined as, yeah. So these 2f1 type solutions are very common. Maybe that is the reason why we are interested in only 2f1 type solutions. And we have second order equation here.
But like, can it happen that second order equation has as a solution f for 3?
F?
For f3.
I need to check that. So
Okay.
2f1.
Well, I suppose hypergeometry functions don't have unique representations.
Yes.
So
we can
the
transform
theorem
that.
he just mentioned out in the next page says that it has one like that.
So maybe the answer is
Yeah,
that.
I'm just asking what are other options.
So because representations are not unique, you could have a 4f3, whatever that is, and then but you can also find one.
If you go to order 3, then we will have 3f2 type solutions and 2f1 type
But
solutions.
it's not unique to those representations.
And a hypergeometric solution, is that the definition? So you get the definition, right? So you
Yeah,
call
that's the definition.
Here.
so this is what you
Yeah,
mean
this
by
is the general solution.
No, that's
what you mean
that's
by
his definition of a hypergeometric
Yeah,
solution.
okay.
Yes.
That's his
Yes.
definition.
And the conjecture is saying about this.
Yes,
This-
yes, that's right. Okay, so now here I stated this conjecture, and if we go to online encyclopedia of integer sequences, we can find a lot of examples like this. And Mark Van Huy and Vijay Kunwar, they tried hundreds of examples coming from online encyclopedia of integer sequences, and they noticed this relation here. So if we start with an integer sequence, and we have this differential operator which is global bounded, and it has hypergeometric solutions. So now we have a motivation to create an algorithm to find hypergeometric solution. But let me say here, so this function, I will call it a pullback function. So this has order 3, degree 3, and by degree I mean the maximum of the degrees of the numerator and the denominator. Okay, so we can find this solution because there are algorithms to find specific solutions. So this algorithm here from Kunwar and Van Huy, if the degree of the pullback function, if it is 3, the algorithm given in their paper can find that types of solutions. But if degree is different than 3, then it will fail. So there are also other algorithms. So here, if we have something called 2-descent, this algorithm can find hypergeometric solutions. And here, if the input operator has 5 singularities, and if at least one of them logarithmic, that algorithm can find hypergeometric solutions. And here, if the input has 4 singularities. So we want to remove these restrictions here. So we want to develop a general algorithm.
So when some of these algorithms couldn't find a solution, does it mean that
It doesn't mean maybe there are hypergeometric solutions, but these algorithms will
they
fail.
just couldn't find
Yeah,
it?
I can give you some examples.
Yeah, but do they know why they could find it?
Why they cannot find it?
Yeah.
But it's not of the type they're looking
Yes,
Yeah, not the
yes,
type.
because the solution is different than, for example,
Oh, okay. Not
Yeah.
not of the type.
He
you
says for
mentioned.
specific tasks, so it just
Yeah.
like doesn't fit into that.
yes,
When you say that like there are 4 singularities, you mean at least 4 or
4 singularities.
Exactly.
Exactly 4.
Ah,
Because,
exactly four.
because they have a table. So.
okay.
And here similarly they also have a table, 5 singularities, but just one of them logarithmic, at least one of them. So we want to develop a general algorithm. Okay, so now before starting talking about quotient method, briefly I just want to define formal solutions and exponents.
My question about those algorithms. So you mentioned that their scope doesn't cover.
Yes.
It's not the full thing. How about efficiency? How fast these algorithms are? Would you say?
They are really fast, so I cannot give you the complexity or something like that, but they are really fast.
With the clock, if you measure with the clock, it's
Yes,
quick?
yes, it is in seconds. I
In
would say.
seconds.
Yeah. So, we want to develop a general algorithm, and let me talk about briefly formal solutions and exponents. We have second-order differential operator, and if we have a number s, it is called a singularity. If it is a root of the leading coefficient or pole of the other coefficients, we will say that it is regular singularity if these two functions are analytic at s. If we have an input which has only regular singularities, it is called regular singular.
What does to the power 0 mean?
Sorry?
What does to the power 0 mean?
Yeah, I mean, it means this is just analytic at s. So I just wanted to state that.
Oh, okay.
I wanted to write the complete formula there. So if we have a regular singular operator, and if we have a point, let's say singularity, then we can compute formal solutions. So the formal solutions will look like this: x minus s to the e1 times the other terms, and the second solution will look like this. Here we might have logarithms, but k might be 0. So these two numbers are called exponents, e1 and e2. Yeah.
Then we have like does it mean a power series in x minus s?
Yes.
Okay.
It is a power series x minus s. If we set s is equal to 0, then this just will be power series in s. So these two numbers, they are called exponents, and I will use this notation to denote the exponent difference. And by exponent difference, we will take the absolute value to make it unique. Okay, so now I can start talking about our first algorithm, quotient method. Okay, so first of all, we have this input differential operator, which has order 2.
By the way, we have enough time.
Sorry? Okay.
To look through carefully the notation and try to remember it for the next slides.
Okay. So we have an input, which is a second-order differential operator. Okay, so first we will start with the special case. And by special case, I mean we will try to find solutions of this type. So the general formula, in the general solution, we have this exponential function times, in parentheses, a function times 2f1 plus a function times the first derivative of this 2f1. So now basically we are saying that we are taking r1 0. Okay, so now we only know L input, and we are trying to find solutions of this type if they exist. Okay, so now if they exist, then we know that there is a Gauss hypergeometric differential operator, L base. So this is my base operator. I will use this notation to denote a Gauss hypergeometric differential operator, which is defined like this. So we need to find 3 parameters to define a Gauss hypergeometric differential operator here. And if our input has a hypergeometric solution of this type, then there exists a Gauss hypergeometric differential operator such that we can connect L input and LB in this way. So this is change of variables transformation, and this one is called X product transformation. So these transformations have effects on the solutions of LB and L input. So LB, this differential operator is Gauss hypergeometric differential operator, and its solution is this 2f1 function. So if we apply change of variables to this differential operator here, we will have another differential operator m, and solutions of this differential operator will look like this. So x will be replaced by f here. And the effect of this x product transformation, okay, so we have this solution, this is a solution of this operator, and after this transformation we will have L input, and L input will have these types of solutions. Okay, so now here L input will be given, and we will try to find hypergeometric solutions of this type. So generally speaking, we need to find a Gauss hypergeometric differential operator, a change of variable transformation parameter f. So m is not important. If we have this, we can compute it. And also we need to find r, the parameter of this exponential part here. So we only know L inputs, but we don't know LB, Gauss hypergeometric differential operator, and which means we don't know those 3 rational numbers, and we don't know f and r. So we will try to find them. If we can find them, then we will we can form the hypergeometric solutions of L input in a special case from the solution of that base operator. Okay, so now I want to start to explain our algorithm by assuming that we have a candidate Gauss hypergeometric differential operator. So let's see what can we do if we have a candidate Gauss hypergeometric differential operator. So this is given, L input is given, and we are assuming now L input has hypergeometric solutions of that form, special case, and we are assuming that that hypergeometric solutions they come from this Gauss hypergeometric differential operator. Okay, so now we have this. We know LB, we know L input, but we don't know F and we don't know Y. So we need to find F and R to form solutions of this operator here. Okay, so we can always compute formal solutions. So we choose a non-removable singularity and we compute formal solutions of LB and formal solutions L input around that singularity. So generally speaking, that singularity is okay, we need to choose a non-removable singularity. Okay, so now we have local information because we can compute the formal solutions up to a finite order. So let's say the order is A. So these lowercase yi's, let's say they are the formal solutions of LB, and these are the formal solutions of LE. Okay, so in the previous slide, we defined the effects of these two transformations. So they will have the same effect on the formal solutions. So these are formal solutions of LB, and after change of variable transformations, we will have these solutions. And after
question.
Yeah.
But how do you know the correspondence between small yi's and capital yi's? So you have pair of formal solutions there, pair of formal solutions there, and how do you match them?
If I is 1 here, so this will be 1. So it will be just that way.
So you can compute formal solution for one operator, formal solution for another operator. You have two solutions here, two solutions here. How do you choose their order?
I see, but we will take the quotient then. So we will. So how do we choose? Actually, we can see that on the exponent differences. So there are theorems. So here
anyway,
we choose.
There are only 4 choices, right?
Yes. So here.
Actually, you can take linear combinations. I mean.
So these transformations have effects on the exponent differences. So by looking at the exponent differences, we can decide that actually.
So they are distinguishable somehow.
Yes.
Okay. And is it special for second order, or this can be in general done for higher order also?
Higher order.
Higher order special operators.
There will be more combinations.
Okay.
So
Okay. That was just curious.
yes. Okay. So. We have this relation between the formal solutions of the base operator and the given input differential operator. So, by looking at the exponents, exponent differences, we can decide if this is 1, then that one will be 1. So here, now we want to recover this function here, pullback function, and we want to recover this parameter R here. Okay, so now, first of all, if you look at these solutions here, if we take the quotient, then the effect of this transformation will disappear there, and the only the effect of this transformation will remain there. So if we take the quotient here, so let's say lowercase q is this quotient, and this is this quotient, so the effect of this, so this product will disappear, and we will only have this. But the effect of change of variables transformation will be there. So which means that q of f is equal to that. But actually these quotients are unique up to a constant. So this constant will appear there. We choose a non-removable singularity, and these quotients will be unique up to a constant. So after taking the quotient, this effect, this product will disappear, and we will only have the effect of change of variable transformation. So now we have this formula with an unknown c in it. So these are series modulo x to the a. But if we, okay, so from this formula we have a formula for f of x, which is given by q inverse of c times q of x modulo x to the a. So now we have some kind of information about our pullback function. But here we have a problem. This constant is a problem now. So if we have this constant, then we can recover this pullback function. But now this is a problem. So,
by the way, so this quotient method, whom does it belong to?
sorry?
Whom does this method belong to?
So this is in my PhD thesis. So my advisor, Mark Van Huy, and we started this quotient method. But before that, they were trying to find hypergeometric solutions, and with his PhD student, Vijay Kumar. So then,
This is your work.
yes.
Okay.
So now we have this C here, and we want to recover this pullback function. So the idea is now, okay, so we cannot try all of the C's because we have infinitely many candidates here. But if we can choose a suitable prime number, L, then we can try C is equal to 1 up to C is equal to L minus 1. Okay, so now we have finitely many candidates. So we want to compute f of x modulo x to the a, L. Then we will use some computational techniques to recover this function f. Okay, so we try each C, we try from 1 to L minus 1. And after each C, we try rational function reconstruction to reconstruct this function here. Okay, so if this works, then for each C again, we try analytic Hensel lifting to lift this function to the higher powers of L. And after each lifting, we try rational number reconstruction to find f, to find this rational pullback function.
How big is your prime?
Sorry?
How big is the prime L?
We start from the smallest prime, so our algorithm usually chooses 11, 13, so it is a small prime. It's not a huge prime, but there are some examples, and we need to go to large primes. So this strategy works if we have a good prime number L.
So in other words, let's say if I do the reverse thing and I choose C to be a very, very large number, is it true then the prime has to be very large? Is there any correlation between the size of L and C? Since you have to try C from 1 to L minus 1.
Yes, it tries from 1 to L minus 1 if L is a large prime and...
No, if C is a large number.
Okay, C is a large number.
But you do Hensel listing.
Huh?
You do Hensel listing. And adding Hensel listing, you can go what
Yeah, we got large powers of L.
You can have L be equal to 3 and still be able to tackle very large numbers.
Yes.
Because least
Maybe there will be other primes that will do the same thing. So here, our algorithm is heuristic, and the reason is that we don't have a good theorem to choose these suitable prime numbers. So for that reason, our algorithm is heuristic, but
in that case, why does he have to try C up to L minus 1?
Because you want to start somewhere.
No, but you said you have a small prime and then you can get a very large C, but C is restricted up to L minus 1 now.
Yes, C is a large number, but we have C modulo small primes also. There will be any
if you want to use the power of L.
Technically, there should be like C bar. So what they try to find is C modulo L.
Yes.
It's just like
It is not C, it is C modulo L. Sorry. Yes.
Okay.
Excuse me.
Yes, that's C, and so this is C bar. Yes.
Okay, all right.
But is it correct that if you have constructed F, then you can check whether it is right? So like it's heuristic, but if it finds something, you can always check.
We can check. We always check.
Okay. So it's like.
So we compute M, and then we try to recover the parameter of the X product transformation. If there exists, if it can find an R, then we will have the hypergeometric solutions.
But if is it the case that if the conjecture is true, then this becomes an algorithm?
So this is not a proof of the conjecture, but this is a good way to check if we have.
If the conjecture is true.
If the conjecture is true,
then this is an algorithm.
But again, we need then this is an algorithm to find hypergeometric solution. But here again, this is heuristic because we don't. Yeah, we have several formulas about how to choose a good prime number L,
So can you turn this to an algorithm by looking through all prime numbers and stop once you found it?
We start from the smallest prime number.
Yeah. And since
we try. Okay. So if a prime number passes all of our criteria, we try that prime number. If it works, then we will have the hypergeometric solution. If that prime number doesn't work, it goes to the next prime number. But we don't have a bound for this prime number, so we don't have final.
You don't need a bound, right? Because you will always find it.
It will always find, but I will say.
Just not because there exists an algorithm.
Yeah, our algorithm can choose a wrong prime number, so we don't have a theorem. If it chooses a wrong prime number, then maybe C will be 0. No, C.
Can your algorithm miss a prime number? Can you skip it?
Yeah, we skip some of the prime numbers, but we don't have a theorem.
So it could be a mistake that you skip them.
Yes.
So could you try random prime?
We start from the smallest prime, and
can you try random prime?
We can also try random prime. So I implemented this algorithm in Maple, and
so do you know the probability? Do you know the probability of success?
Yes. So most of the time it will succeed.
That's good.
So because we tried these examples from online encyclopedia of integer sequences.
That's from experiment, not from theory.
It is not from the theory, it is from the experiment. Okay, so here we have this rational function, but our algorithm also recovers algebraic functions. So the idea is same, but formulas will be different. But we can also recover the algebraic functions with the same method. So if we have f, then we can compute m. Then it is not hard to find the parameter of the x product because there is a formula for the second order operators and there are algorithms. Okay, so this strategy works. So as I said, we tried maybe more than 300 or 400 examples from different sources, from physics, online encyclopedia of integer sequences. It works. Yeah.
But you had, as far as I understood, you described an algorithm with assumption that you know LB. But how do you find LB?
That is the next question. We don't know LB.
So it's like half sentence.
Yes.
Okay.
This is the next question.
Okay,
so this algorithm will work if we have LB, but one part is missing in our algorithm, and it is this LB. So, or we need to find these three numbers, which defines LB. Okay, so now how to find candidates for LB. So this was a huge problem. This was a combinatorial problem because we might have too many candidates. Okay, so this
A1. You solved a huge problem.
Yes.
That's good.
So we have A1, A2, and B1. We need to find those three numbers. So those three numbers, they define our Gauss hypergeometric differential operator. So Gauss hypergeometric differential operator, it has three regular singularities at 0, 1, and infinity. Alpha 0 is the exponent difference at 0, alpha 1 is the exponent difference at 1, and alpha infinity is the exponent difference at infinity. So if we have alpha 0, alpha 1, and alpha infinity, we will have three equations in three unknowns, so we can choose candidates for A1, A2, and B1. Okay, so and also we know that if this operator, the given operator, if it has hypergeometric solutions, then there exists the Gauss hypergeometric differential operator. So we need to find it. So we don't know the exponent differences. So let's say they are alpha 0, alpha 1, and alpha infinity. But this is given. So let's say we compute the singularities S1, SR, and these are the exponent differences of L input at those singularities. So again, we can create a set. So this alpha 0, alpha 1, alpha infinity will be elements of this set. So they will be in this form, A over B. A is 1 or one of the exponent differences of this set. And B runs from 1 to df. What is df? Df is the degree of f. What we don't know f. But we have a bound on degree of f. So we can compute a degree bound for this pullback function. We can choose specific Gauss hypergeometric differential operators, and we can guess.
What does degree mean when f is algebraic?
Degree mean the maximum of the degrees of the numerator and the denominator. So that is the degree.
But that's rational.
Yes.
If f is algebraic.
F is algebraic.
Does it mean
I see.
Is it the minimal polynomial or what?
This is the degree of the extension.
So it's the minimal polynomial
Yes.
degree.
So
So degree have two meanings.
We have algebraic degree and degree.
Okay.
So
it's the same thing as DF? So DF is either one of them or what?
It is not either one of them. So let's say we have Q of x.
Well, you can take the bigger one, of course, all right.
Yeah. So we have this formula here. We don't have f, but we can compute a degree bound. So this is the formula. This is the set for rational pullback functions. But if you have an algebraic pullback function, again we have a similar set.
Oh, I see.
We can put the algebraic degree here,
right.
and we can run from one to algebraic degree bound. Okay, so now here, at least we know how to choose candidates for alpha 0, alpha 1, and alpha infinity, but this set might have too many elements.
So excuse me for my ignorance. Are these numbers A1, A2, and B1, must they be rational?
Yeah, they are rational numbers.
They have to be rational for the hypergeometric.
Yes.
You can use other numbers. You can use other parameters for hypergeometry other than rational numbers?
I don't think so. So we use rational numbers.
But
You use rational numbers.
why not? It will be well-defined power series.
A1, A2.
Like
The
square of
Polynomial
2.
symbol, so we have Polynomial symbol there. Yes, sorry, yes. But this is
Maybe he meant just for an algorithm, for the sake of being part of like input of an algorithm. He wanted that to be rational numbers.
Okay.
Possibly.
Could be.
Conjecture.
All right.
okay. So now we have candidates for alpha
So
0.
the real question is, maybe the A1, A2, B1 are not rational. Then what is this doing? I mean, if it is allowed, I don't know. That's why I claim ignorance.
Don't ask me.
Okay. Anyway, all right, let's go on. Let's go on.
Okay, so now we have this set. So we need to find, we have candidates for alpha 0, alpha 1, and alpha infinity. But the problem is now this set might have too many elements. So we need to somehow eliminate the number of elements in this set.
Are you assuming that these A over B is in reduced form? Reduced fraction?
Yes. GCD of A and B.
Yeah,
You
do
mean
you
that
assume
this is
that they're
one?
reduced form? Okay.
So we have this formula. So we have in my thesis and also one of our papers. So it is called Riemann-Hurwitz formula for differential equations. So this is a special case for our purposes. So if we have these differential operators LB and L input, so they are connected in this way. We have these two transformations. LB is a Gauss hypergeometric differential operator.
Would you clarify? So is this theorem a special case of someone else's theorem, or is this a new theorem?
There is a very similar theorem. So let me see. I don't remember the name of the authors of the paper, but I can show it here. So
could we see the conclusion first?
yes.
Okay.
So now we have this conclusion here. So we have a relation between exponent differences of LB and exponent differences of an input differential operator. So here this df is the degree of f. So this has no effect there. So we have this formula, and now we have this set, and we have this formula. If we use this formula for, okay, so we choose alpha 0, alpha 1, alpha infinity from here. So we don't know the degree of f, but we have a degree bound. So we choose a number. So we have alpha 0, alpha 1, alpha infinity, and a candidate degree. If they satisfy this formula, then it gives us a candidate Gauss hypergeometric differential operator. Okay, so with this formula now, this formula eliminates the vast majority of the candidates in this set. Now we have a manageable number of candidate Gauss hypergeometric differential operators. So we sort them with respect to the candidate degree. So we always try to find the hypergeometric solution with minimal with pullback function with minimum degree. Okay, so now we know how to choose candidate Gauss hypergeometric differential operator. So I implemented this algorithm in Maple. So fine to have fun. So the first step, compute candidates. then compute quotients of formal solution at a non-removable singular, then use modular reduction, hence lifting, and if they exist, find R, then if they exist, find a hypergeometric solution, form the hypergeometric solutions, or return an empty set. So these are the general steps of our first algorithm. But this algorithm solves the special case. We are trying to find hypergeometric solutions of this type, so these are rational numbers. If R1 is 0, then this algorithm is very effective and it can find the solutions.
So if the algorithm returns empty list, what does it mean?
It doesn't mean there isn't hypergeometric solution. Maybe R1 is not equal to 0.
But does it mean that there is no solution with R1 is 0? So is it guaranteed that it is
I am not going to say it guarantees because we don't have a theorem on the prime numbers.
Okay, but after that, okay.
Yes. So if we have a good theorem, and also we don't have a bound on the number of Hansel lifting steps, so that part is also missing. If we have theorems for those cases, then I can say that if it returns an empty list, then there is no hypergeometric solutions of this form.
So right now you don't know how many primes you have to try, right?
We don't know.
Right. So you just arbitrarily say, "Oh, I give up."
Yes. So there are some initializations in my implementation on the number of Hansel steps and the digits of prime numbers. If it exceeds that step, then algorithm returns an empty list. But maybe, yeah, we need a theorem for those two parts.
Have you actually seen it return the empty list?
So far, the examples that I tried, we could be able to find hypergeometric solutions. But there is one example, so it ran maybe more than 2 hours. So it was doing something. It was constructing these Hansel lifting steps, but it didn't return the solution and it didn't return the empty. So I just interrupted it. But we need theorems for the prime number selection and this number of Hansel steps. So otherwise, except for one example, I would say we could be able to find solutions of this form if R1 is equal to 0. Okay, so now the next part will be creating an algorithm for the general types of solutions. So now R1 is not equal to 0. We will assume that R1 is not equal to 0. So what can we do? So one idea is that we can try to simplify the input differential operator first. Then we can run this algorithm. So this will be the idea. So simplifying is almost equal to solving. So what do I mean by that? I will give you an example here. So now I want to talk about integral basis. So maybe I should give an example for this statement, why simplifying is almost equal to solving. So here, we have this example. So this is an order 3 differential operator. So this comes from a physics paper. So here...
It was like that in the physics paper. Is this how
it is on the physics paper.
Like that?
I
was
can't hear you.
Exactly like that?
Yes. It was on the appendix.
Okay.
So this is an irreducible, and let me show you what do I mean by simplifying is almost equal to solving. So I used.
Do you recall what kind of physics problem this
is? It comes from the Ising model. So electromagnetism. So I don't have the detail, but that equation comes from the Ising model. So yeah. So now here I use the Maple's dissolve command, and it cannot solve this differential operator, but I simplified it using integral basis. So these two third order differential operators are equivalent. So the same command now works. So this is what I mean simplifying is almost equal to solving. So we will do something similar. So here, let me give you one more example. So let's consider this number field. So here we have this defining polynomial which has a large coefficient. So let's say we have a problem here, a computation problem in this number field. So one way to solve that problem, we can try to find an isomorphic number field with with a nicer defined polynomial, and we can transform our problem to another problem in this isomorphic number field, and we can try to solve them. So the key step to find an isomorphic number field is computation of an integral basis. So this is an example, but in general we have this set. A is the set of irreducible polynomials, and we have this equivalence relation. F1 is equivalent to F2 if and only if these two number fields are isomorphic. So the goal in the previous slide was, given F1, find F2 with small bit size such that F1 and F2 are equivalent. So I will call F2 a standard form of F1. So we have more than one F2. So those F2s will be called a standard form of F1. So these F2, these irreducible polynomials, are equivalent to F1, but they have smaller coefficients. So this problem here...
Does the isomorphism there only mean that they have the same dimension over Q?
They're isomorphic number fields.
Function fields.
No, are they fields or just?
They are fields.
They are fields?
Because it's reducible polynomial in one variable.
Yeah.
Oh, in one variable.
It's one variable.
So F2 is a standard from F1. So this problem here, it has a solution, and it is the polynomial reduction algorithm from Cohen and Diaz. So the first step is this algorithm compute an integral basis, then apply LLM to find a nice transformation. Okay, so now one application of this algorithm is that we can reduce computations in this larger number field to computations in this nicer number field. So it doesn't solve the problems in here, but it simplifies. So now let me talk about a similar case. So we have D, ring of differential operators with rational function coefficients, and we have A. A is the set of irreducible differential operators. So we define this equivalence relation, L1 is equivalent to L2 if and only if these are isomorphic as D emojis. So this is very similar. And now our goal will be given L1, find L2 in A with small bit size such that D over dL1 is isomorphic to D over dL2. So similarly, I will say L2 is a standard form of L1. So one of the application. Okay, so now.
Question. There is a question.
Yeah.
So, do you still minimize bit size, not the degree? You minimize bit size, not the degree.
So it is
small.
Coefficients will be smaller, and it will have. So we will remove apparent singularities from L1.
So, but like you think that x to 100 is better than number 1 million as a coefficient?
Yes.
Could you explain what you mean by bit size?
No, you see, the degree is the same.
Yes, the order of the differential operator will be same.
Because the two fields are isomorphic.
No, I mean degree in x.
Yeah, they're the same.
F1 and F2.
So the coefficients will be nicer, L2. So L2 will look like nicer. For example, in the previous example, I had this third order differential.
Non-commutative ring.
Bit size is counting the coefficients and everything.
Yes.
How would you exactly define
I
it?
don't understand the discussion.
So in the how can I say? So it will be easier to do computation with L2.
Bit size is just how much storage you need to store the information.
Is that exactly what it is? What is bit size?
So it will be easier to compute with L2. So do computations with L2. So we can compute.
I see.
How can I say? Yeah, maybe I should have used
Give an
the bit
example.
size there.
Give an example.
Yeah, the example was a third order differential operator there. So it has large coefficients and it computes. It has one. It fills the one screen, but we find L2 a standard form. So it has small coefficients, less apparent singularities, and yeah.
And what Gleb was asking, you could have your new thing with larger degrees, right? But with smaller coefficients.
Yeah.
Larger degrees with smaller coefficients. So you mean L1 has a large order?
No, L2. Which one is new?
No, they can't.
L2 is new.
It's new.
L1 is new.
So your L2 could have coefficients of larger degree than L1 does, correct?
No, I think they're the same because they have to be isomorphic. Come on.
Okay.
Degrees, orders are the same, but the coefficients,
So
this will have smaller
Is
coefficients.
cubics fixed?
What about the degrees?
because they
Orders are the same, they are the same order.
yeah. the same order.
Same order.
Yeah.
But
Degree in X.
Oh, the degree in the
X.
coefficient.
Don't you
X.
fix the coefficients
X,
with the
not in D,
isomorphism?
degree in X.
I see.
Yes, it's over.
Yeah, it will be
So
smaller.
you could have a high degree.
It will be smaller, so we will remove some of the apparent singularities from there.
so it will be smaller.
Yes.
Okay.
It depends on L1. So if this is in the standard form, then they will have the same degree.
Yeah.
Okay.
Yeah.
Yeah, I think they should.
So
Especially if it depends on the
Same
previous equivalence of the F1 and F2.
yeah, if L1 is a nice operator, then maybe L2 and L1 they will be the same. So now our solution idea to this problem is imitate the Polynomial algorithm, because we have a similar problem. We will try to imitate the Polynomial algorithm. So the first step, compute an integral basis, then use the LLM. So we will try to do something like this. So now, one application, we can reduce solving a complicated, large differential operator with large coefficients. We can, so the application, we will reduce the number of apparent singularities of L1. So L2 will have less apparent singularities than L1, and we will try to solve L2. And L1 and L2, they are equivalent.
So what's apparent here mean?
Apparent singularities?
Yeah.
So they are the singularities of L1, and the solutions are unended there. So, okay, so now computation of integral basis for algebraic number fields and function fields, they are well studied from Trager, Cohen-Diaz, Van Huy, De Jong, Mons, and Stillman. But the differential analog is new, and it is given by Manuel Cavers and Christoph Kucher in 2015. So now we give an integral basis algorithm which is faster than the algorithm given in 2015. And in addition, we will normalize the basis at infinity. So this algorithm will first compute a global integral basis, but then we also need to think about the point at infinity. So this corresponds to the second step of the Polynomial algorithm. Okay, so here, now let me define this integral basis here. Then I will talk about the algorithm. Okay, so we have L. So let's say it is a regular singular. So and now order might be different than 2. So if you compute the formal solutions of this differential operator at a singularity, it will have a basis, and we can write these basis elements in this form. So here Ts is the local parameter x minus s, or 1 over x, and pi's are in here. So here, this number, we will take this number and we will say that this is the valuation of this solution at s. Actually, we only take the real part because it might be a complex number. So if we take the real part. Okay, so here, maybe, okay, so if it is not here, but let's say if the real part is greater than 0 or equal to 0, then we will say that this function y is integral for this given differential operator. But this is not what we want. We want to define integral differential operators. But this, we will use this valuation here. So now let's say we have L. So order is n, and let's say we have another differential operator g. Okay, so let's define the valuation of g at one point s like this. So here, y is a solution of n at the given singularity, and we compute the valuations of g of y's. So if the order is okay, so this is we can only look at the basis elements here, those solutions. So if the infimum of these valuations, if it is greater than 0 or equal to 0, then we will say that this g differential operator is integral for L at one point. So now we can consider all of the points, and then we can say that g is called integral for L if its valuation is greater than 0. So now let's form the set of integral operators for L. Let's say this is the set of g's which are integral for L. So this is a CX module, and a module basis of this OL is called an integral basis for L.
Is the existence of G given an L guaranteed?
Given an L,
that it is integral.
Yes, it is guaranteed.
It's guaranteed that there is an integral.
Yes, we can find, yes.
Could you maybe give some intuition behind that? What?
So we define the valuation.
How should I think about this integral basis?
Okay, so we have a differential operator L.
Okay, yes.
So let's compute its solutions, and let's say we have another differential operator.
Okay.
So now we compute. Okay, so y is one of the solutions, and we have this g. So we compute this here, g of y, and we compute its valuation here. If that valuation is greater than 0, then we will say it is integral.
Wait.
Yeah, I see the definition, but like, what's the reason of stating such definition? Like, why is it good? It's not a mathematical question. It's more
I see.
like,
Yeah.
No.
So here, so we apply this g to the solutions of L. So they are, generally speaking, gauge transformations. So they will help us to transform the given differential operator F. An integral element, a differential operator, it will correspond to gauge transformation, and it moves the exponent differences, exponents of the solutions of L 0 or greater than 0. So it's actually a gauge transformation. By applying that gauge transformation to given differential operator L, we will find equivalent operators. And this, okay, let's say we have -5 as an exponent, so we will make it 0. And after this transformation, since they are integral, actually, okay, let's talk about the basis elements. So their evaluation should be less than 1. If they are greater than 1, then it is not a basis element. So we can find another basis element. So we are trying to move all of the exponents between 0 and 1, except for the infinity. Then we will do something for the infinity.
But the evaluation of G at S is taken over an infimum.
Yes, but
as Y varies, is that right?
Yes, Y varies. Yes.
So
it should be minimum, right?
So it can be greater than 0, but need not be an integer. Infimum need not be an integer. Is that correct?
So here y is a solution. Maybe I should try the minimum here. So y is a solution, and we can only take look at the basis elements.
Look at the basis.
Yeah.
Oh, okay.
So we have found out the minimum.
So it's just
of
minimum.
y's.
Yeah. Just minimum. Okay.
Okay. So in a similar way, we can define local integral bases. So here we are looking at all points in C. But if we have a polynomial P, we can only look at the roots of that polynomial, and we can define local integral basis. So this set will be a local integral basis if it is a module basis of this set here. So G is integral for L at every root of P. So instead of looking all of the points in C, we can only look at the roots of a polynomial. So we can take this polynomial as like x minus s, then we will have a local integral basis at one point. So this is a set of differential operators which are integral for L at the roots of this polynomial. So it is a local basis now. Okay, so now we want to compute this basis because these integral elements will give us will give us transformations to transform our given differential operator L. So now we want to compute this basis. Okay, so in order to compute this basis, we only need an algorithm to compute a local integral basis at one point. And that point is 0, then we can use change of variable transformation to find local integral bases at other points, and then we can combine those bases. So we have a theorem. So B1Bn, it is a local integral basis for a differential operator L at x is equal to 0. If we have, okay, so first of all, these elements here, they should be integral. So this item number 1 says that the valuation of these elements here, they are greater than 0. But this is a basis. So their valuations should be greater than 1. Which means that if we have these numbers here, so all of them are different than 0, then this combination, the valuation of this combination should be less than 1. If it is greater than 1, then we can multiply this 1 over x, and we will have another integral element which cannot be written in terms of this. So then it is not a basis. So it means that if this is not satisfied, one of the elements in the basis is wrong. So now these valuations are greater than 0 and less than 1. So this is a theorem, and this theorem actually gives us an algorithm to compute local integral bases. Okay, so the main, okay, so we initialize in the algorithm, we initialize B1, and then we define B2 in terms of B1, and then we form this ansatz, and we locate the non-integral terms, and we find the coefficients of those non-integral terms, and if those coefficients has a solution, then we will have another candidate for B2. So I'm not going to explain this algorithm in full details, but generally speaking, so this here helps us to find local integral bases.
But when you said this is for all C1 over Cn, so that means you can pick any C1 over Cn, anything you want?
C1, Cn?
You said for all.
For all C1,
not for some,
Cn.
but for all, you said. Because it doesn't matter, because it's, I see. Because the valuation only depends on B1 or Bn and not the coefficients.
I see. Maybe I forget x here. So. No. Yeah, so, yeah, if these are, let's say, 0, 0. Yeah, if they are all 0, then this is 0. But if one of them is not 0 and this is greater than 1, then that element is not a base element because we can divide it by x. So, yeah, they might be,
let me put my question some other way of how to use the theorem. I'm not.
I see.
So how to use it? So presumably, if I choose a different vector C1 over Cn, I will get a different J. Is that correct?
Different C1 and Cn.
Yeah, I'll get a J depends on the given C1 of Cn or not.
No, it does not depend on. So J is here. J is one of the solutions of the.
But that's the way you write.
Yeah.
You didn't say that there exists a J such that for all this happens. You know what I'm saying?
Right.
Yeah, there exists one J such that if this happens.
There exists a J.
So not for all. Yeah.
So the for all it should be at the back.
Exists.
Is that the back?
Sorry. If that exists,
No, I just want
this
to know what,
combination, then
I just want you to tell me what this statement is saying. What does it say?
I see. So it shouldn't be for all. So yeah. So if we have this, which is not 0, and this modulation is less than 1 for 1j, then one of the basis elements is not correct. So it means that. So if this is a basis, then for all constants here,
No,
this
I'm
modulation
simply
should be less
asking
than 1.
you whether J that there exists depends on the choice of C1 over Cn.
That exists j. So it's not. No, it does not depend on the choice of C1, Cn.
So the way you write it should be there exists a J such that this thing is true for all C1 over Cn.
Okay, so
Is that correct?
No.
there exists one j. Okay, so you want me to move this here? There exists one j such that for all this,
Yeah.
this happens.
Yeah, is that what you mean?
Is there a single yj that
That's right.
works for all of
All
those
the vectors,
all of
all
those
the
things?
choices that you pick, other than 0.
No.
I see. So if we have one solution, let's see, and this happens. I see. So there exists one j. If you can find just one, if this
Could it be
happens,
some? Yeah, you mean there exists a C1 over
yeah,
Cn?
there exists. Yeah.
Or some
Sorry.
C1 over Cn?
Sorry,
Okay.
yes, yes.
All right, that's what I'm asking. Okay.
Okay, so yeah, I can talk about this later after the talk because I see something here now. Okay, so
I just wanted to see what it says. That's all.
So I'm not going to talk about the algorithm in full detail. So we use this theorem to compute local integral bases. But let me talk about our improvements. So we have two improvements on this integral basis computation. So we don't compute local integral bases at the pair singularities because these local integral bases can be given by d to the e1 and d to the en. So e1, they are the exponents of the apparent singularity. So one, if our algorithm encounters an apparent singularity of the most common type, then simply it uses this formula. It does not compute local integral bases. So this saves time.
Excuse me, what does our EM mean?
It is the remainder of d to the e1 over L input.
Oh, you mean in
Right
the,
division. Yeah.
in the okay.
So, and the most important improvement is this algebraic non-rational singularity. So let's say we have an algebraic singularity with a polynomial p. So we compute a local integral basis b1, bn for L at one of the roots of this polynomial. And we don't compute integral basis for the conjugates. So what we do, we want to scale these bases in such a way such that this basis, okay, so this new basis C1, C1b1, Cn, Bn will be automatically a local integral basis at the roots of, at all roots of that polynomial. And these coefficients are can be given by like this. So if we choose these coefficients, okay, so we compute a local integral basis at S, but we don't compute the local integral basis at conjugates of S. Instead of we scale these bases in this way, then it becomes the, okay, then we take a trace, then this basis, this new basis is a local integral basis at this polynomial. So this strategy here saves a lot of time because we do computations in QS. And it, let's say degree of this polynomial is D, so, but in their algorithm, Kawes and Kuchen, so they also does computations with the conjugates of S. So they do computations in Q, S1, S2, up to SD, which might have degree less than we call D factorial. So there's a huge time difference between two algorithms, and this is one of the main reasons. Okay, so we compute, okay, so this is just the general outline of the algorithm. So we compute local integral bases first, then we combine these local integral bases to find the global integral basis. Okay, so here I just want to show you this table just to be complete. So I said our algorithm is faster. So these 17, okay, so these are, I use 17 examples coming from 2 combinatorics papers to compare the running time of the 2 algorithms. So here, the differential operators, they have algebraic singularities and apparent singularities. And now, with these 2 improvements, we can see the huge time difference between these 2. So maybe I should say, so this is in Mathematica, this is in Maple. But it shouldn't have so much effect on this. So
no, there's a big difference because Mathematica is interpretive, whereas Maple you compile.
I also implement their algorithm on Maple, so the timings are similar. So
Have you tried to compile the Mathematica code and then run it?
In our algorithm in Mathematica?
Yeah, no, in the Chaos algorithm. You said the Chaos.
I implemented their algorithm in Maple, not our algorithm in Mathematica.
He implemented their algorithm in Maple.
So both are in Maple, you're saying?
Okay, so these timings are in Mathematica, this is in Maple,
Yeah,
but if I use Maple, then it is similar to that.
What?
He's saying that he also implemented their algorithm in Maple.
Well, where is the data then?
Okay, so he does not have
Maybe
data
I should have,
displayed.
maybe I should include that data, right?
Yeah, because you can compare Mathematica with
He
Maple.
can, and so he compares, but
Well, that's not the numbers you should present.
Huh?
That's not the numbers you should present.
Well, so he chose to present these
Well,
numbers.
that's wrong.
Huh?
That's wrong. Because you're comparing apples and oranges.
This is
Mathematica is
this is your
interpretive.
opinion.
Mathematica is interpretive, so therefore it takes longer.
Oh, I
It's
see.
okay, just your opinion about this.
No, that's a fact. Come on. That's a fact.
What does interpretive mean?
He chose to present
Means
this
that you
way,
take
that's
every
how he
line
presented.
and you check and you work on every line instead of compiling a program, let's say eventually into C and then run it, which is far more efficient. Because you optimize it by the compiler. Your code is optimized.
Okay, so
I see.
Yeah, sure.
That's actually the way you presented it.
I see.
It's still interesting because so there is a ready-to-use product in Mathematica. You produce a ready-to-use product in Maple.
Yeah.
You substitute the same thing into each of these and compare. So this is a valid comparison
No.
because
No.
it's some existing product. You use it as a black box,
Yeah.
and somebody else is using your product as a black box.
Yeah.
And compare.
But you-
So
but
which
you
product-
I see.
which
but you
product
can't-
would you
yeah,
like
I see,
to
yeah.
use?
But you can say that their calculation is less efficient than your calculation, but you cannot say that your algorithm is better than the other algorithm.
I'm not sure he's saying that.
Oh, he's
Yeah,
saying
but
that.
this-
He certainly is saying that.
Yeah, but this algebraic, doing computation with algebraic singularity, so it says,
No, I'm sure you're even right,
I see.
okay? But the way you present the table,
Okay.
I would suggest that you actually implement them in Maple.
Insane.
But
Okay,
then
I see.
compare.
I see.
Or you implement yours in Mathematica
I see,
and
okay.
compare. Otherwise, you know,
Yeah.
it's like you're using 2 different machines, right? And then give the data.
It is not like, because the user would be interested.
Yeah, it
is.
depends on the user. Then, yeah.
Of course,
It's
it
what
depends
actually
on how.
Yeah, I see your point.
The
yeah.
impact on user.
All right. I don't want to
The
argue
user
with
is
you. You don't
using
agree?
that.
Fine.
Yes.
Fine. Okay.
Okay, so now let me
We
talk
should get
about.
Wolfram here.
Okay, so
See what he says.
now we know how to compute global integral bases. So now the basis elements they are integral at finite singularities. So, but we don't know anything about. But we haven't done anything about the point at infinity. So infinity might be a singularity. So let me define this. So let's say we have this set. We will call that this set is normalized if there exist functions here such that after this scaling, it is a local integral basis at that point. So this set is normalized at S if we can find functions like this. Then okay, so here it is a local integral basis. So now we have our global integral basis, but we don't know, we don't have any control on the point at infinity. So we want to scale our global integral basis in such a way that it will be close as possible as being integral at the point at infinity. it is not going to be a local integral basis at infinity, but it is going to be very close to being infinite. I mean, the exponents, we will make them small as possible. We make them as small as possible. So we want to normalize our global integral basis at infinity. So just let me give you an idea. So this normalization of an integral basis for algebraic function was introduced by Barry Trager. So we used a very similar method, and we followed his method for the differential case. So it is very similar. So now we can compute global integral basis, and we can also normalize this basis at infinite. So those basis elements will give us gauge transformations, and we can transform our input differential operator to another one. So we will make the exponents at finite points between 0 and 1, and then we will have this normalization to make the to control the exponent at infinity. Okay, so now let me return our two problems. So simplify a given differential operator and find hypergeometric solutions. Okay, so simplification is just imitate the Polynomial algorithm. Now we can compute a normalized integral basis. Okay, so these basis elements will give us transformations to simplify our input operator, but sometimes a linear combination of those basis elements will give us a better transformation. So this algorithm does also that. So it checks, and if it can find a better transformation, it uses if it can find a linear combination, if it can find a combination of the base elements, it uses that transformation to simplify that. So one of the examples that third order differential operator. So we use this algorithm, and we found a standard form of the third order differential operator there. So I can show you this example. Again, but let me talk about this second part. So find hypergeometric solutions. Okay, so now we have an input. So this time it is a second order differential operator, and we are trying to find solutions of this form. So we can combine our standard forms algorithm and find to F1. So for a given input, we first use find to F1. If it can find the solution, then it returns the solution. If it cannot find the solution, if it returns an empty set, then we try to simplify our differential operator using a standard forms algorithm. Then we run find to F1 again. So here is the idea. So this R1 comes from a gauge transformation there. So so this standard form algorithm, it finds gauge transformations to simplify L, so it makes this 0. Then we compute the solutions of the simplified version, and we form the solutions of the input from the solutions of this operator here. Okay, so now I have two examples. Okay, so let me show you this. So this is okay, so this is, this equation also comes from a physics paper about Feynman diagrams. So actually this is the linear part of a nonlinear differential equation, but we will try to find hypergeometric solutions. So this is our implementation. So first it tries find to F1 program, but it returns nothing. But it does not mean it does not mean there aren't hypergeometric solutions because it can find only specific type. Then we run our standard forms program. We compute integral basis and normalize that basis at infinity. Then it transforms the input differential operator to another one. It finds hypergeometric solution of the special case of the simplified equation, then it forms these solutions from that simplified equation. So this is this equation also comes from a physics paper, and this comes from a combinatorics paper, but here our algorithm does the same. So it tries find the F1 program first, but it returns nothing. Then it simplifies, and it solves the simplified equation, and it forms these solutions from the simplified equation. Okay, so that's all. Thank you very much for listening to me.
More questions?
Thank you.
Thank you again.